All right, good morning, soon to be good afternoon, chemistry students. It's still, for me, Friday, March 20th, but I am making the last kinetics lesson for next week. So getting ahead here. Here is your do now for the day. 2 questions. I've gotten rid of the answer choices. Why don't you click pause on the video, think about what's behind these blue boxes, think about the unit that these questions are asking about. Try to make any connection you can to the question and maybe anticipate what the answers might be. All right, pause the video, go for it. All right, welcome back. So number 6, this one does appear on a lot of Regents questions. They do ask like pretty bluntly, just, hey, do you know where the metalloids are? And you should remember that when you see this word metalloid, it's the dividing line between the left side of the table, the metals, and the right side of the table, the non-metals. And you should be thinking about that black staircase. Okay. Now, there are 6 metalloids according to the New York State chemistry curriculum that you need to know. Sometimes different textbooks classify different elements a little differently, but we need you to know that there are six metalloids. There are 4 on top of the stairs. Let's just add another one there. So there are 4 on top of the stairs, and then there are 2 that are underneath. Okay, and I'm trying to think here in position, the way I've drawn these. There should be 1 here and 1 here. So there are 6 metalloids, 4 of which stand on top of the staircase, and then there are 2 that are underneath. So hopefully you go to your Google chemistry reference table, or you go to Google Classroom. I posted it in the materials a long time ago. So you have your reference table, you find those 6, and hopefully match it up to an answer choice. Okay, the next one is chemical property of iron. So if you're making some connections here, iron is Fe on the periodic table. So you're thinking about element Fe, okay? And then you're obviously gonna, there's really not much more than this phrase right here, chemical property. So what are chemical properties? So you should definitely be thinking about what those are. And if I'm thinking about chemical properties, I'm thinking about how it reacts. And when you think about how something reacts, you think about how does it sort of get rid of, or what does it do with its electrons? Does it want to share electrons? Does it want to transfer? Does it want to give away electrons? Does it want to take electrons? So you're thinking about valence electrons, and you're thinking about how something like reacts. How does it change to form bonds? All right, so let's get rid of those blue boxes, and then we'll see if we can get to the answer. Okay. All right, so which of the following elements is a metalloid? Well, pretty straightforward. The only one of these elements that are one of those 6 metalloids is silicon. So the answer to this one is number 4. And number 7, which statement describes a chemical property of iron? How does it react with other substances? So let's skip the first one. Your answer is going to be number 1. But let's get to the rest of these and why they're not right. Iron is a solid at STP. So that tells you that it's a solid at standard temperature and pressure. That is a physical property. That's not describing how it bonds with other substances. That just tells us what it's doing at standard temperature and pressure. So that's a physical property. Iron melts. It can melt. It would have to be very, very hot, but iron can go from a solid to a liquid. That's a phase change. Phase is spelled P-H-A-S-E, phase change. And I always remember that phase changes are physical changes. You are not deciding how iron forms a bond with another element. Melting is a phase change, and all phase changes are physical changes. So that's not a chemical change or a chemical property. Iron is attracted to a magnet. If you took iron and you attract it with a magnet and it sticks, and you separate them and you stick it again and you separate them, it's still iron. It's not changing form. It's not changing its chemical composition. It's just a physical property of iron. So the answer is iron oxidizes. And what that means is iron, if you didn't know, oxidize means it reacts with which element? Oxygen. So Fe will react with oxygen and form Fe2O3. And that is iron oxide. So that is actually changing. When you go from iron to iron oxide, that is the process we know as rust. And you know that iron is very strong, rust is very weak. So they have very different chemical properties. They have very different chemical properties when it goes from iron to iron oxide. So the oxidation of iron is a reaction of iron with oxygen. That is a chemical property. Okay. All right. Moving on. Our objective today is to label arrows on a blank PE diagram. You need to identify all PE values on a PE diagram, and you need to explain verbally and in writing how they know whether a PE diagram is exothermic or endothermic. Good news is this is a very easy lesson. It's got a bunch of vocabulary that you're gonna have to like take note of. But unlike Le Chatelier's principle, the lesson from yesterday, unlike some of the equilibrium stuff, conceptually, I don't think this is too difficult to understand, but there's a bunch of new words and new ideas, but they're pretty easy to implement. So it should be a pretty good lesson. Here's your meme of the day. I thought that was pretty funny. I'm making my own memes as of late. So we definitely don't want you guys here. We want you guys down here. We want your brains doing all the online learning and doing all the work. So there's your meme of the day. All right, let's preview today's lesson. This is a turn and talk. Let's scoot this back over here now. Turn and talk. So this is at the center of what we're talking about. So before I even teach you what it is, what it means, why don't you pause the video and think about where are the reactants in this? Where are the products? Where do you see this thing having the lowest energy and the highest energy, and why? What is happening? Take a minute and see if you can digest this diagram. So I'll pause the video, think about as many of the answers to these questions as you can. All right, so let's just very briefly go through this, some of the basic answers to this question. We don't need to go too deep because we're going to talk about a lot of these, in more detail at the middle and end of this lesson. But basically, you should see that this is a chemical equation. It's got two arrows, so it's one of those reversible reactions where you have a forward reaction and a reverse reaction. So you got A and B plus C turning into A and C plus B. What kind of reaction is that? That's right, it's a single replacement reaction. So you have A and B and C separate, forming A and C plus B, but the reverse can happen. A and C with B by itself can go back into A and B plus C. So it's a two-way reaction. Now, you can see that there is a relationship between the reaction that's listed in the chemical equation and what's left over here in this diagram, right? So you see that AB plus C appears here, okay? And then you also see that AC plus B, which are the products, appears here. So there's a connection between this diagram and what you see in the equation. So you should be able to take what you remember from these equations and apply it to this diagram. Where are the reactants? Take a minute, think about it. Well, if these are my reactants in the equation, then these are my reactants over here in this diagram. Where are the products? If these are the products in my equation, then these are the products in my diagram, okay? And then in terms of low and high energy, you see that this diagram here, this graph shows, let me use yellow. You see that this features reaction coordinate, maybe we don't know what that means, but it also features energy. So the higher up we go on the y-axis, the more energy we have, right? So you would say that the highest energy would be, where on this graph is it the highest? The highest energy might be here, and the lowest energy might be here with my products. So we're going to try to give you some definitions, and we're going to show you some of the basics on how to interpret this graph, and we're going to tell you what the heck it's all about. That's what today's lesson's about. So you probably already know a bunch. Here we go. So kinetics, part 2, potential energy diagrams. You guys will like this. I think it's pretty straightforward. I want to be clear. Potential energy diagrams are not phase change diagrams. Phase change diagrams, they always get mixed up with by students. Phase change diagrams like here, this is going all the way back to Unit 1. MC delta T, MHF, MHV. You're talking about the phase change diagrams for water. You should be able to identify melting points and boiling points with this type of diagram. You should be able to determine when kinetic and potential energies are changing and staying the same. That's all a review of stuff we did a long time ago. That is not what we're referring to with potential energy diagrams. Potential energy diagrams are the things you were just looking at. Okay, these are potential energy diagrams, and sometimes for short, I'll call them PE diagrams. They show us the energy that, how the energy changes during the course of a chemical reaction. And they are not phase change diagrams. They are potential energy diagrams. So make sure you have that straight. Okay, Potential energy diagrams, as I mentioned, they tell us about the path of reactions. So where is the energy the highest? Where is it the lowest? Why do you think that is? So take a minute. I'm going to pause this, maybe answer these two questions and on your own, see if you can figure them out, and then we'll go over them. So I'm going to pause the video now. All right, so hopefully our last discussion there when we sort of previewed this diagram should give you some of the answers that you're looking for. Where is energy the highest? Well, you should immediately turn your attention towards the y-axis, okay? And the y-axis shows us right here that that is the axis that deals with energy. The higher up you go on that axis, the more energy you have. So where is it the highest? It's at this middle point, okay? And you're looking at an energy of about 100 kilojoules. So that's where it's the highest, right at this point. Why do you think that is? What's happening at that point? What do you think is going on there? So take a minute, think about that. Pause the video if you want. So this is the highest point in energy because it's at that critical phase when the reactants are coming together and they're just about to make that shift to form products. So it's at that middle zone when you are not quite your reactants anymore, you're not quite your products, you're all smushed together and you're ready to start the actual act of changing all these bonds, which is requires a lot more energy than just existing as reactants or existing as products. So this is your highest point in terms of energy. We're going to talk a little bit more about that. We're going to talk about what this is called, but this is just a preview of this diagram that we're going to spend a few lessons talking about. All right, what I need you to know for today's lesson, potential energy diagram. It's a diagram that shows potential energy changes during a reaction from reactants to products. So it shows how the potential energy changes as you go from left to right, from reactants to products, okay? You can pause the video if you want to copy that down. I don't really need you to copy that down. I think we'll do so much work with PE diagrams that you'll just sort of know this, and I'm not going to test you on this specifically. So if you want to pause it and scribble it down, you can, but we're going to move on. Okay, now this is something you absolutely need to know. There are two types of potential energy diagrams. Take a minute, definitely pause the video, look at these carefully, and think about the answers to these questions down here. So pause the video and answer as many of these as you can. All right, so at this point, hopefully it's pretty clear. You see that these two graphs, these two PE diagrams are different in one big way. In one case, the energy goes up from left to right. So you have a lower amount of energy on your reactant side, you have a higher amount of energy, and in this case, energy from reactants to products increases. On the other hand, you have the opposite. You have a higher amount of energy on the reactant side, and you have a lower amount of energy on the product side, so the total amount of energy will actually decrease. So these are two big differences. So the potential energy of the reactants is lower than the potential energy of the products. And then over here, we're going to say the potential energy of the reactants is higher than the potential energy of the products. So you're going to need to know the difference. And here is your definition. Okay, exothermic, a reaction that loses energy. You end up with less energy than what you started with. Well, where did it go? How did you start with this much energy up here, whatever this value is, and you end with only this much? Where did that energy go, right? Where did all that amount of energy go? It was lost, okay, to the environment. It was released. So a reaction that loses energy. I would definitely sketch this. And when you see a graph, a potential energy diagram where the energy goes down from left to right, you need to be able to classify that as exothermic, okay? On the other hand, you have the opposite. You have endothermic, and that's a reaction that gains energy. Well, you only started with this much, but you ended up with this much. So you gained this much energy, okay? Well, where did that energy come from? So we're gonna say that energy was absorbed. That energy was taken from the surroundings and it was used by the reaction. So an endothermic reaction is going to gain energy. And what I need you to know is that if you see a potential energy diagram that goes up from left to right, you must be able to classify that as endothermic. And there's a lot more to it than that. We're going to talk about it in more detail, but that's the first thing I need you guys to know. Endothermic versus exothermic, okay? Make sure you pause the video if that was too quick. You watch it again and copy these two sketches in your notes. You will be asked to know that. All right, now the real heart and soul of today's lesson should be pretty easy. There are 6 arrows that I will ask you about on these PE diagrams, and they are super common on the Regents as well. The Regents exam will give you a diagram like this with 6 arrows with a little letter next to it, and it will ask you for the names and or the values of each of these. So we're going to start with 3 today, and we'll do the rest on, well, probably next week. So we're going to talk about these arrows and values, and today, as per the objective, they are all about potential energy. If you notice, these 3 arrows are all under the curve. They go from the x-axis to the graph in 3 different locations. 2 of them are pretty obvious. That third one in the middle there is something we talked briefly about earlier in the lesson, but I need you to be able to tell me the names of each of these arrows and their value. The value is probably pretty easy, but let's just go through one at a time. All right, arrow A is called the potential energy of the reactants. Again, the way I remember it, any arrow that goes from the x-axis all the way to the graph, and touching the underneath part of the graph is going to be a PE arrow. So arrow A is called the potential energy of the reactants. You might abbreviate it PE of the reactants. And that should be pretty self-explanatory because you remember that this area were my reactants, this area was my products, and this was that middle ground. So anything that's on this side of the graph might deal with the reactants. Anything that's on this side of the graph will deal with your products. So A is the potential energy of the reactants. B is what's called the potential energy of the activated complex. So that special area that's at the highest point of energy on this graph is called the activated complex. And then letter C is the potential energy of the products. So these are the 3 potential energy arrows that you need to know about. Now, the names of the arrows is one thing, the values of them is another. So why don't you take a minute while I erase this really quick, see if you can determine the value of each arrow, how much energy is at each of these arrows. So why don't you take a minute and try to figure that out. Pretty much labeled it for you guys. So the potential energy of the reactants, as you can see, will be 40 kilojoules. So this is 40 kilojoules. KJ is your unit, kilojoules. Sorry, pardon my ugly writing. The potential energy of the activated complex is 100 kilojoules. And last but certainly not least, the potential energy of my products is only 20 kilojoules. Okay, so let's do a quick pause here, quick sort of check for understanding. Why don't you pause the video and tell me, does this represent an endothermic or an exothermic reaction, and tell me why? Pause the video. All right, so this absolutely should represent an exothermic reaction. You're starting with more energy than what you're ending with. So the energy is going down from left to right. Energy is being released. Maybe if you're good, you can even quantify how much energy was released. And if you take, 20 minus 40, you'll see that you have lost 20 kilojoules of energy, but that's for a later day. This is an exothermic reaction because the energy went down. All right. Show me if you guys can do this. We'll do a couple practice questions and then we are done. Okay, I'm going to pause the video. I'm going to ask you to label the names of each of the arrows as well as the quantity of potential energy. All right, pause it, go for it. All right, so I'm not going to write it in because it takes a while to scribble it all down. But like I said, I'm not trying to trick you guys here. It's pretty self-explanatory. A, remember, this is the reactant side, this is my product side, and this is that activated complex. So A will be the potential energy of the reactants. B, again, I wasn't trying to confuse you. B is all the way over here. That's my potential energy of my products. Remember, before I say this, and last but not least, C is my potential energy of my activated complex. Any arrow that goes from the x-axis all the way to the underneath the belly of the curve is a PE arrow. So this is the PE of the reactants, this is the PE of the products, and this is the PE of the activated complex. Now, I will actually scribble down the values. How much energy was it? And again, it doesn't say it here, that's my fault, but you should know the values are almost always going to be in joules or kilojoules. We'll use kilojoules for this one. So what's my value for my PE of my reactants? It should be 75 kilojoules. What's my value of the PE of the products? That's 225 kilojoules. And then last but not least, what's my energy for the activated complex? It's 300 kilojoules. All right. All right. Nearing the end of this. So let me go back really quick, very quickly. Tell me, endothermic or exothermic, and how do you know? Pause it for a minute. Think about it. Look at your notes. I'm not even going to pause it. I'm just going to wait. So this should absolutely strike you as an endothermic reaction. Okay, so the energy is lower on the reactant side than it is on the product side. Energy goes up from left to right. So that's an endothermic reaction. This is an endothermic reaction. It absorbed energy, it gained energy. All right, one more, then your exit slip will be posted. Okay, again, name the arrows, tell me the values, and then we'll go. Pause the video. And we're back. I'm just going to do it verbally very quickly because I would imagine this is getting pretty easy. A is the potential energy of the reactants, and it has a value of 20 kilojoules per mole. B is the potential energy of the activated complex. It has a value of 100 kilojoules per mole. And C is the potential energy of the products, and it has a value of 50 kilojoules per mole. Okay, so our objective today was to simply label all the PE arrows on a blank PE diagram. I'll ask you guys to do that. I would like you to identify all the PE values on a PE diagram. So tell me how many joules or kilojoules of potential energy each of those arrows represent. And then also tell me whether the graph represents an exothermic or an endothermic reaction. So quickly going back to this one that we looked at, exo or endothermic? It should be endothermic. Again, you have a smaller amount of potential energy here on the reactant side. So the graph goes up as you go from left to right, meaning this gained energy, it absorbed energy, it's endothermic. All right. All right. I am going to show you your exit slip. There's a little bit more going on here. I will post this on a Google Doc for you to label and to answer. I look forward to reading your responses. That's it. That's the first week of kinetics. I hope you guys have a great weekend. If you have any questions, email me and we'll come back next week and we'll do the finishing touches on this unit. All right, guys. All right. Have a great day.